Thank you. So good morning, or afternoon, I suppose. First off, I know you have competing opportunities here and presentations to watch today, so thank you for choosing to spend your time with me, and I'll do my best to provide a high-quality presentation. So today, I'll be presenting work that I've done with TechCast, so I want to thank them for allowing us to share all this data and information with you. So the purpose of the paper today is really to look at, as society evolves and we're focused more on climate change, and wherever you stand on this, the science is what it is, and whether or not that matters, society is starting to form an opinion, and we need to adapt and modify our practices to keep up with popular requirements. So utilizing flexible or smart automation will allow you to really put a high quality product in the beginning of your foundry and see the gains throughout the entire line. And that's what this paper is about today, is the downstream benefits of increasing the quality of the product going into the system. So before we get into that, I want to give you a very brief history of MPI and where we've gotten to today, or how we've gotten to this point. I think it's really important because this is primarily, most of our automation's gone into high-end customers, aerospace customers. A lot of my customers don't like me sharing information of their successes with anyone, frankly, even internally sometimes. So I thought I'd give you a quick history and really understand that we've been doing this a long time. Since 2004. So we've been doing this for 20 years. This is the first automated assembly cell that we put into the market with pine tree casting. That then evolved into what we call our 2014, which is really the gold standard now for automated assembly and has replaced the 2010s out in the world. We've since then developed automated injection. What's nice about this is it's not only duplicating what the operator is able to do at the machine, but also in some cases increasing what's able to be done at the machine, such as serialization of the parts live as they're coming out. So you can really track a defect right from wax all the way through. And these are fully customizable based on what the requirements are of our customers. We've developed fully custom, specific, very job-specific automated assembly cells. This one is for single crystal assembly specifically. This is an assembly cell that is designed specifically to do, and is running today, like IGT components, so lower volume, but high mix, multi-plane, multi-level welds, and utilizing a full 3D scanning so that we can get an optimal position every time, even with the varying runner. And from all of that, we've taken all that we've learned and we've really developed what we would build for ourselves working with a commercial customer. And this is the piece of equipment, or one of the pieces of equipment we'll focus with today. So we've been working with TechCast, who is a local foundry near us. They're about 4 hours from MPI. They are commercial, low volume, high mix, ferrous metal foundry. And they came to us because they want, they're having labor problems, they're having issues getting supply out, and they need a higher quality and they need to step up their game. So we thought this was a good opportunity to share real world results with all of you. So for our first production run, we had a small part. It's only 0.11 kilograms per finished metal pattern. We ran a total of 13,500 parts in this first, so everything that you're seeing is based off of 13,500 patterns. The test, we had 3 assemblies. So one of the things, the flexibility of this automation allowed us to do this. So this is a baseline assembly, 80 parts per tree, right? 8 parts per row, 5 rows on each side. And we ran 5 of these as a baseline. So this mimics what our customers been doing and been running for years. It's the same spacing, it's the same layout. It does have the repeatability because we did do this on the automated cell. Next, we decreased the spacing and put as many parts as we could on this tree. So we're now doing 90 parts on a tree, so we added an additional row. And we shipped 140 of those assemblies fully finished. And then lastly, to round out, we wanted to set up for success going forward because we believe we'll be able to do better than that 90 parts per assembly. So we made an assembly with 106 parts. Now, previous to now, this wasn't possible, and that these are essentially the same assemblies, although we have added an additional 8 parts per side. And because this automation is now putting one part on at a time, we're able to vary the orientation of the rows, the number of parts per row with a fully automated solution. It takes, first time setup is about an hour for a tree. Once it's there, that's in the recipe. Now we can run any of these 3 assembly mixes with the push of a button and selection of a recipe, just like you would with the wax press or any of your other equipment. We shipped 150 assemblies in total. And this is the existing process that we took over. So that on the left is a Model 44. It happens to be the machine that they were running. This is a horizontal, we would call it an automatic press. It's actually the one they have is pretty beat up, so they weren't running it in full automatic. But it's a machine capable of producing parts, dropping them into water, and then you have an operator standing at the end of the conveyor, removing the patterns, trimming the patterns, inspecting the patterns, and moving on to the next step, which is a manual assembly. And they were building 23 assemblies in a day, and it took 3 people. So 2 people assembling and 1 person running the injector. So come to MPI, when we took over this project for them, we put it onto a horizontal, what we would call our 2006 automated injection cell and our 2012 automated assembly cell. And right away that brought us to the point where we're doing 25 assemblies per day with 1 operator running both pieces of equipment. What we're really here for is what are the gains in all of this? So the gains in wax injection, what's nice about the automation is it really brings out the bottlenecks, and this equipment is designed for optimal product flow. So in a perfect world, we'd all run single piece flow. We all know the first thing we do is put multiple parts onto a tree. So we don't ever really do single piece flow, and this equipment is designed to match the optimal flow of the foundry that's using it. Reduce operator tending with the automatic nipping. So the injection cell, in this case, we are utilizing it to nip the patterns, and because it's handling every pattern individually and moving it out of the way, we never are getting any damaged patterns from falling on top of each other or handling, and they're coming out to the operator ready for assembly. Again, no breaks or discards. When we first got this, and I will say that this is very common when we work with a customer and we get a tool for the first time, we always ask the question, how is the tool? And they say it's great, one of our best tools, it's ready for automation. It became very apparent this was a well-loved tool with 750,000 cycles on it, and right out of the gate, although we were getting good injections, we were getting 52% scrap. We were able to clean the die. So this is just how we got it from our customer. We cleaned the die and instantly reduced down below 19%. Unfortunately, the die was reasonably damaged, and we will, going a little slow. All right, so the die was damaged. We'll be able to reduce that well below 5% once we replace some of the damaged components of the die, but it is damage coming to us. When running these parts by reducing the spacing, we saved, well, running the automation, we're down to 44.5 hours saved labor. We decreased the pattern spacing, increasing the density, and we were able to reduce the total number of assemblies needed by 19 for this production run, or 12.5%. That means there's 19 less pour cups used, 19 less runners being assembled, 19 less trees being made, and total wax saving of almost 30 pounds or 13 kilograms. This is an example of the spacing reduction. We went from 12.7 millimeters to 3. Now, something that often comes up is we can't cast that, it's too close. So I ask is, if this was a part geometry that your customer came to you with, would you say, I can't do it, or would you figure out how to achieve? And what automation does is it allows you to have that consistency in an assembly that you would have in an injected pattern, right? So this is the geometry they're doing today. So we know right out of the gate, maybe we can't go as close as we did, maybe you can. We certainly can go as close as that hole is in diameter. Gains in the shell, again, reducing 19 parts, reduce number of dips required. Because there's 19 less trees, their bottleneck is 160 mold capacity, or 11% of capacity. I just ask you, what is the value if you had to go and buy 11% of your shell room? 38 minutes labor saved, just loading and unloading the trees. 0 part fallout. This is important. We see this on all of our automation projects. The consistency and the strength of the weld results in 0 parts breaking off in shell. Gains in shell, so we do see a lot more bridging when we do this. This is often perceived as a weakness. What we have found in practice is it's really a strength, and it does allow you to use less shell, and you get a stronger shell faster. So by reducing those 19 trees and increasing the spacing, we saw a gain of 37.4 or 374 kilograms. We did see a slight decrease or increase in the amount of shell used per pattern when we went to the larger density. And it really then becomes a question of what's the right density for you and your facility. We will be moving to a higher density with TechCast in the future. Gains in metal. We increased the pour ratio. It's a very small part, so it wasn't a huge increase. 2.8%, 6.7% if you use the higher density tree. Again, 19 less trees, so that's 19 less heats, 19 less dewaxes, or a batch in each in their case. We're estimating that we're saving 82 kilowatt hours of energy in just metal melt. There's other additional energy that we're saving throughout the rest of the facility, but the metal melt's a big one. Post-processing, saving 95 minutes in knockoff, assuming 5 minutes to knock off a tree, 19 less trees to cut off, assuming 15 minutes per tree, saving 4 3/4 hours. What was notable is the operators came back and talked to their manager and pointed out that they had less cutoff damage because the consistency was so good that they didn't have any cutoff damage, and they were able to get all the parts in one go and get a closer cut to the gate, which means less downstream processing as well. In the future, we'll be looking at automating that, the cutoff. So total gains as a recap. Total savings, 52 man-hours for 150 trees. 374 kilograms of shell material that doesn't need to be mined, transported, mixed, or put into your vat. 289 kilograms of metal saved. 82 kilowatt hours of energy saved. A little over 11% capacity saved in the shell room, which is their bottleneck process. Reduced wax defects in the wax and cutoff. We often see a decrease in scrap. This was a very well vetted part, and they really had the assembly. Their mix was, they had a very low scrap from casting defects, so we didn't see a gain in this one. It was a pretty robust part from that standpoint. And then ancillary benefits, increased capacity, consistency in wax welds. It leads to downstream gains, improved customer delivery performance, increased capacity, reduced labor requirements. And in this case, because we're delivering it, it was $100,000 that they wouldn't have been able to ship our customer month, right? They had no way of producing this, so it was an injection into their facility, which is pretty nice. Future work, we're going to continue to reduce the number of shell coats. We're gaining that extra strength by bridging faster, so we'll reduce the shell coats. Run additional part numbers with smaller batch sizes. I mentioned in the beginning, this machine's really designed for small batch runs. This was the first part that we're running with this customer, and they just wanted to start with one part number. Bring automation in-house, so that'll save, we're really developing a process that they're able to take on and onboard on their own and look to automate the cutoff in their facility in the future. One of the things that we have noticed as we've been running this equipment is that really smart, intelligent automation leads to easier onboarding of new employees. We do a real deep dive into that, actually at the last ICI. If you're interested in that, I'd say take a look at it. I won't go into it now, but we're able to bring in a brand new operator off the street and in a matter of minutes have them out producing any senior level operator. That's been a real big gain for us because when we have a good employee that we know, I don't have to stick them to wax assembly. I can move them anywhere else in the facility and gives us a lot of flexibility as a business. So with that, any questions? I think I ran a little long. Am I fine? All right.
Yes, you have some questions from the audience for Aaron? One on the back.
It's a hard setup to see the timing, so I apologize if I rushed that a little.
Yeah, thanks for sharing that. I'm curious, as far as a low volume, high mix shop, how do they succeed in automation when a lot of the shops I walk into don't know if they're going to have that part or any foresight for how long? If you have any comments on that.
Yes, that's a good one. The question is, how do you utilize automation if you're really low volume, high mix? This machine, so our past automation has always picked up an entire row, which required really high quality runners and a lot of high volume. This machine now, we're picking up only one part, so we use a much more generic tooling, so the tooling cost is very minimal. The trays are just made out of a bar stock, and the machine really compensates for any variation in the runner. Additionally, we've built what we're kind of calling our intelligent automation or smart automation, and it's really designed in the software end to make it so an operator, someone who has no robot experience in a couple hours can be trained to set up this machine. And then once somebody's set up the machine a couple times, it takes our operators about 20 to 30 minutes, maybe an hour to set up the first time. And then once it's been set up the first time, then it just runs. So in our shop, if I have a customer that wants 5 assemblies or more, that's around my cutoff. It skips the manual bench, goes straight to automation, and once it's in there, that's my break even. After 5, if I see it again in a year or in a week or 10 years or never again, I'm never losing money on it. And it's just as easy as loading a recipe. And I don't have to have any history or memory on that part, right? The process lives in the machine and I get the same quality, same rate, same run rate every single time, no matter when I run that, whether or not I get it back. Any other questions?
Yeah, Aaron, thank you for the presentation. I was wondering, most of the foundries, and at least in Europe I see, are very, very busy and the resources quite stressed, and the resources as well. So how do you handle it? How do you, such a big project, to get the automation going and get to...
So I think keeping the automation simple and modular the way we've kind of developed it, and that's how we're using it as a... the tooling is very low cost. We have generic trays, so if we get it in, it's a generic tray. Again, it's a couple hours of training for an operator. So you have the person in your wax room already that can program the machine. It's been brought down as a kind of a stepwise to walk you through it, and we provide the training. But again, that's the difference of just bringing in a robot and saying, how do we make this work, as to having a fully fleshed out product that is designed to set up and be repeatable and robust, and once it's set up, it never changes. And for the real low stuff, you just use generic tooling, so that way you don't even have a tray cost anymore. But it's designed for someone you already have in your facility.
Thank you for sharing those automation applications today. So my question is, we know the robot arm, the accuracy of the robot arm is about 0.5 millimeter, is very accuracy. But however, our casting parts, the trees, our pattern wax, the geometry variance is way above those accuracy. How do you to make those things together to overcome the geometry variance?
Really, in the way we're picking it up using a single draw, like the variation in the pattern is less than the variation in the gripper, right? So well, not variation, but the gripper it'll overshoot by more than the variation in the pattern, right? So if you have some variation in your pattern size, the gripper is going to grab something that's smaller than the minimum pattern will ever be. And then we're scanning and looking at the runner. So as the runner varies, we have a video of it that, we can take inches of variation, far more than any facility would ever put through their system. So from the runner standpoint, it just adapts to the runner. And what we find is, as people get more into it, they say, all right, well, now we can make a higher quality runner and we'll get more gains, right? So it brings out the bottleneck. You start seeing, once you put it in automation, it really, I find it opens up what your true variables are, right? So I would say, today your operator is the biggest variation you have. And this is bringing it down to the robot, fraction of a millimeter, or the wax shrink, which is negligible, right, is your biggest variation. So by pulling that out, you're able to see where the other areas are. And part of the reason we saw the defects in the die, right? So I hope everyone takes that away is, big gain in this was just take care of your tooling, like have good tooling. There's a lot of capacity there, right? And, for me, as an equipment manufacturer, I want you guys to have the best tooling in the world, because then you're going to need a machine that can keep up with it. If you have tooling that creates defects, well, is it the machine? Is it the wax? Is it the tool? It's hard to dissect, but that balanced flow, I know that machine's going to build 4 assemblies or 6 assemblies an hour. And I know that my injections can keep up with that. So I don't even need to be the operator looking. As a manager, I just walk out. I know what it can run. It's in the machine. The machine tells me. And I just look and go, it's been 30 minutes. We didn't make 3 assemblies. What's wrong? And for me, at MPI, we always blame the process, not the people. Right? So what's wrong with the process with breaking down? And very quickly say, we're throwing away a lot of wax patterns, so we can't keep up. Why? Right? And then we fix the root cause. I hope that helps. Any other questions?
No more questions?
Excellent. Well, I really appreciate everyone's time, and I was really thinking that I would have like 2 people in here because I know they got the economics over there. So I thank you all for your time and sharing it with me. And yeah, thank you. If you have any more questions, I'm here.
Thank you, Aaron.